Rigid transformations, just a little more practice, especially on rotations, which I think oftentimes students can use. So throughout American history, quilters have used transformations to create intricate geometric designs. For example, the quilt to right is an example of a design based on the rotation and reflection, while the quilt at left contains translations, rotations, and reflections. In lesson 313, you found ways to locate the image of a shape after it's reflected. Today you'll work with your team to develop ways to describe the image of a shape after it's rotated or translated. So what they're going to ask us to do is open resource page 314, which essentially just looks like this, and we have to perform these things. And again, this is how I like to do these. So if I go, obviously, like we have up, down, left, right. Well, if I go 180, it's going to look like this. This will be up, this will be down, and again, these are like the new ones, right? This will be my new right, this will be my new left. So to get to this point, I didn't move. To get to this point, I had to go left 3, so the new left 3. To get to this point, I went left 4 and up 1, so left 4 and up 1 will be right there. To get to this point, I went left 1, 2, 3 and up 1, 2, 3, so I'll go to the new left 1, 2, 3 and the new up 1, 2, 3. To get this point, I went left 1 and up 1, 2, 3, so I'll go left 1 and up 1, 2, 3. To get to this point, I went left 1 and up 1. Here I just had to go up 1. So you can see I get something that looks like that, and it does look like a 180-degree rotation. Now what's interesting is it doesn't matter if I rotated clockwise or counterclockwise, it's going to be the same, right? So again, this will be my new up, this will be my new down, this will be my new right, and this will be my new left. So here I had to go up 1, so the new up. Here I had to go left 1 and up 1, so left 1 and up 1 will be right here. Left 1 and up 3. Left 3 and up 3. Here, left 4 and up 1. And here, just left 3. So I get something that looks exactly the same as A, which makes sense because a 180 doesn't matter. But now let's say I go 90. Well, this would be my new up, my new down, my new left, and my new right. So to get to this point, I had to go left 1. And a lot of kids don't know where to put this point. But again, left 1, well, my left 1 is this way now. Here, left 1, up 1, 2, 3. I'm going to go left 1, up 1, 2, 3. Here, I had to go up 1, 2, 3, 4. So my new up, 1, 2, 3, 4. And finally this point, right 1 up 1, 2, 3. So right 1 up 1, 2, 3. So I am going to get something that looks like that, and you can see it definitely looks like a 90-degree rotation. What if I go 90 degrees this way? Well, this will be up, this will be down, this will be left, this will be right. Again, I go left 1, so I'll go left 1. Left 1 up 1, 2, 3, so I'll go left 1 up 1, 2, 3. Here I didn't go left or right, but I did go up 1, 2, 3, 4, so up 1, 2, 3, 4. Here, right 1 up 1, 2, 3, so right 1 up 1, 2, 3. And you can see, again, it does look like I rotated it 90 degrees this way. So they're looking pretty good. 270 this way, 90, 180, 270. So you can see up, down, left, right. It's going to look exactly like this one, right? The up goes over here, which makes sense. 90 degrees this way is the same as 270 this way. So left 1 up 3, left 1 up 3. No left or right, but up 4. No left or right, but up 4. Right 1 up 3. Right 1 up 3. And you can see, just like we expected, it does look the same. Here, 360, well, it'll look the same. Here, 180. So to get to this point, I had to go right 1 and up 1, 2, 3. So think about it. This is up, down, right, left, right? So I went right 1, up 3, right 1, up 3. I already have a point. Here, right 1, down 1, 2, 3, right 1, down 1, 2, 3. So this one will also look the same. And then here, if I go 90, it doesn't say which direction, but again, it shouldn't really matter if I go this way or this way because it's a square. So let's just go this way, up, down, left, right. I went right 2 and up 2, right 2, up 2. I'm moving points, right? left 2, up 2, left 2, up 2. Left 2, down 2, left 2, down 2. So that one's not going to change either. The last three are almost like trick questions. Alrighty, so let's go to 339. What I've done on 339 is I've taken the liberty of writing all this stuff down. And I'm going to open a coordinate plane and do this, but I'll read this before I do that. So definition of rotation. So what exactly is rotation? If a figure is rotated, how can you describe it? Investigate this question below. Graph paper, we're going to graph points 4, 1, and 2, 5. We're going to use tracing paper, although obviously I'm not going to rotate 90 degrees. I'll use kind of my strategy for rotating 90 degrees. Counterclockwise, that's important. I need to remember to go counterclockwise about origin. It's important I have to have a point to rotate from. So they give me origin. I'll make points A prime and B prime. I'll draw all the line segments back to origin, and I'll compare the lengths and the angles formed. Then I'll predict the measure of this angle, A prime. And then I'll start looking at the lengths, and I'll see if I can figure out some things about the lengths and the length measures as I've done. And that is what I will do for 39. So I will set that up right now. Asked us to do is plot these points and then rotate them 90 degrees. So this would be my new up, this would be my new down, this would be my new left, this would be my new right. So to get to point A, I went right 4 up 1, so I'll go right 4 up 1. This will be my A prime. To get to B, I had to go right 2 and up 5, so I'll go right 2 and up 5. This will be my B prime. I hope we're okay with all that. Again, did that a few times. So they asked me to connect all these points back to origin. As a matter of fact, you know what I'll do? I'll make like the B's one color, and I'll make the A's another color. That might be easier to sort of make some of the comparisons that they're asking me to do. Okay, so now it says compare the lengths and angles. Well, here's what I think. The length should be the same, right? I mean, it just makes sense that if I copied this length and rotated it over, if I had to go right 2 up 5, don't forget our slope triangles, right? 2 squared plus 5 squared should equal 2 squared plus 5 squared. And or the square root, right? We're using the Pythagorean theorem, sort of pretending that we're making right triangles here. So 2 squared plus 5 squared would equal this hypotenuse squared. Well, I get the same thing here, 2 squared by 5 squared, right? The square root of that. Here, it's 4 by 1, and it's 4 by 1. So I know that these lengths are the same. And these angles should be the same as well, meaning this, that the angle to the x-axis should be the same as the angle to the y-axis, right? So here I go over 4 up 1, here I go, actually I should say up 1 over 4. So if I make this the new up, I'm going up 1 over 4. So you can see those angles are the same. Same thing to get this one. I had to go up 5 and over 2 to get this angle. So if I make this my up now, I'm going up 5 over 2 to get this angle. So you can see those angle relationships are similar. To get back, I've just swapped the y-axis for the x-axis is all I've done on those. Next, what they want us to do is figure out what do I think the angle is for this, for the A0, A prime. Well, I think it's 90 degrees because I rotated 90 degrees. So let's see. My slope here is up 1 over 4. So my slope here should be down 4 over 1 if I'm right? Negative reciprocals, down 1, 2, 3, 4 over 1. There we go, we have our negative reciprocals. This is a 90-degree angle. It asks us, hold on, there's supposed to be a point P. Let me pause real quick and see. I'm having trouble with my notes. It says, why does it make sense for all points P? And I was like, I don't have a point P on this graph. It's just saying generically, why does it make sense if you have a point and you rotate it 90 degrees that the angle between them would be the angle that you rotated? So really what they're saying is this. If I take this point and rotate it 90 degrees, well, shouldn't the angle be 90 degrees? That's how far I rotated it. That's what they're saying there. And I'd say, yeah, that does make sense. And then it asks, like, what about the side lengths, right? What about this length? Does it make sense that this length would be the same as this? Well, yeah. I mean, if I took graph paper and I just rotated it up, that length would be the same. Or same thing here. If I had this length and I had wax paper and rotated it, of course that length would be the same. By the way, that is known as preserving it. So you keep it, right? When you preserve vegetables in a jar, you're keeping them for later. So when we preserve a side length, we're keeping it that same side length for later. So I don't know. I honestly think that question is more confusing than helpful in some ways. I think it takes something that is so obvious and almost makes it a little bit confusing to sort of understand. All right, so the last thing we're going through, we have those, and we're in 340 now. So 340 says, definition of a reflection. Now that you know more about slopes of parallel and perpendicular lines, revisit the reflection from 325 and confirm the relationships. So find the diagram in the resource page, but I'm probably just going to do it here because it's essentially this. And at least I'll have the words here so I can kind of go through and mark this up as I go. Which shows PQR reflected across line L to form P prime, Q prime, R prime. Use your ruler to draw 3 dashed lines, segments. I don't think my lines will be dashed, but that should be okay. So essentially what they're saying is, let's go ahead and connect P to P prime. Let's connect Q to Q prime, and let's connect R to R prime. It says use your ruler to draw these 3 segments. What is the relationship between these segments? Well, I think they're all parallel. So if they're all parallel, I need to have the same slope. So here I go down 2 over 4. That's a slope of -1/2, right? Q has a slope of -1/2. So R is down 2 over 4. So that also, down 2 over 4 is -1/2. R has the same slope. And what about P? Well, P is down 1 over 2. It's hard to tell because we're not on lattice points, but down 1 over 2. And again, hey, look, they all have the same slope, so I know that these lines are all, or these line segments are all parallel. So they're parallel. And I verified that they all have the same one. Now focus on line segment R, R prime. So just this one right here. It says, what's the relationship between the line and reflection? Well, I think that's a 90-degree angle. And again, I know the slope is -1/2. So this would have to have, this line of reflection would have to have a slope of 2. Because if I'm saying, hey, R prime has a slope of -1/2, and I want the negative reciprocal of that, it would be positive 2 over 1. So this needs to have a slope of 2 over 1 to be a 90-degree angle, up 2 over 1, up 2 over 1. So yeah, I can confidently say those are perpendicular lines. So no question, I'm looking at perpendicular lines, not because they look like it, but because I have proven it using the slopes. And there's a big difference between saying they look like it or I've proven it. So there we go, we have perpendicular lines there because of slopes. So use slopes to confirm the reflection. I already did. So I'll say I already did that. I just did it. Place point N at the intersection of R and R squared. So we don't really need, we know they're perpendicular, so that's kind of in the way now. So they're saying put point N here. What do you think is true about Rn and Nr? Well, I think they're the same distance. So 1 squared plus 2 squared equals x squared. 1 squared plus 2 squared equals x squared. So yeah, these are the same length. I can tell by my slope triangles that they have to be the same length because of Pythagorean theorem. I can calculate it, but it's irrelevant. It's the square root of 3, but it doesn't really matter. That the fact is that they're the same. So is what you deserve for line segment R true for all of them? Well, here we get 1 squared plus 2 squared equals 1 squared plus 2 squared, and here I get a half squared plus 1 squared equals a half squared plus 1 squared. So yeah, I'd say yeah, it is. If I reflect the parts that get cut in half are indeed equal. And that does make a lot of sense because the distance from here to here should be the distance from here to here. That was 314 part 1.